Hello, everyone. Welcome to another VPHi Keynote Webinar session. I am Mojtaba, and I'm the host of this session today from Biomechanics section, KU Leuven, Belgium. Today we have Professor Tony Keaveny here. Dr. Keaveny is a professor of Department of Mechanical Engineering and Bioengineering at the University of California, Berkeley, and also a co-director of Berkeley Orthopedics Biomechanics Laboratory, which is established by him at 1993, and is one of the pioneers in the field of orthopedic biomechanics, mechanical behavior of bone, and design of bone implant systems. So today's keynote talk is about virtual stress testing for osteoporosis assessment from bench to bedside. Please, I ask the attendees to ask their questions in a question box. I will ask them in the end from Professor Keaveny. I don't want to spoil the presentation, but actually, Professor Keaveny is the founder of one of the very first companies and spin-offs to develop an FDA-approved simulation-based product for clinical diagnosis tests. And we know how valuable it is, so here we want to see more about it. So Professor Keaveny, the floor is yours, please.
Thanks very much. I'm going to switch everybody to the slides, and then I'll come back for Q&A at the end. So it's a pleasure to have this opportunity to speak to the group, and let me just disclose, as mentioned there, I started this company, Owen Diagnostics, and I have an interest in that company. See. All right, so what I want to start with is the motivation for the work that I'm going to present. So the motivation here, I'm going to talk about motivation. I'm going to talk a lot about the underlying science and the journey going from the technology in the lab to taking it to something that is actually available for clinical use. I'm not going to dwell too much on the technical details, but I am happy to answer any questions when we get to the end. So the context for the technology that we developed, which we call biomechanical computed tomography, or BCT for short, is a problem in the field of osteoporosis, in which the problem is that, of course, many people as they get older get osteoporosis, which is a weakening of the bones, and I'll show you more on that in just a minute. But the detection of osteoporosis is weak, and as a result of that, not many people that should be tested are tested, and therefore the preventive measures that you could take to stop hip and spine fractures from occurring and other fractures, those are just not taken. So you have lots of hip fractures, spine fractures occurring that really should be preventable. And a hip fracture is a pretty nasty way to go, because about 20% of people die within a year of getting a hip fracture. So for many people, it actually signals the end of life. Also in orthopedic surgery, there's applications where you really need to assess the quality of the bone before the surgery, especially for spine surgery. And the current technology, which is called DEXA, dual energy absorptiometry, it's a two-dimensional scan that you can see on the left here, and it can provide reasonable information on the hip because there's no bones before the femur. But in the spine, the images are, the technology is very limited because there's a lot in the way of the vertebral body which you want to assess. You have the posterior elements are showing up in the image, and if there's any degeneration or arthritis in the facet joints or in the spinal region, it all shows up as bone mineral density, which gives you false positives. So DEXA is the dominant test that's used to diagnose osteoporosis, but it's limited. People don't get tested enough with DEXA, and the test itself, being two-dimensional, has some inherent limitations. So BCT is based on, as you can guess, a CT scan, and it's fully three-dimensional in that respect. So it has the potential to work better than DEXA, and I'll show you some data on that. But by combining the image that you can get from 3D medical image processing with finite element analysis and biomechanics principles, you can actually virtually stress test the bones and make measurements of the breaking strength of the bone. So here you see for the femur, we extract the femur and then we rotate it into a sideways fall configuration, and then we load it the way it would be loaded during a fall, and then we can measure the breaking strength. The colors there show where the bone tissue is failing under the loading. And for the spine, we load it with a compressive overload. Now on the spine, you can see that we have a layer, that there's a top layer of plastic placed on top of the vertebral end plates, and that simulates what we do in a compression test in the cadaver lab. So the tests that I'm showing you here are tests that simulate what we do in a cadaver lab. And the question then is, how well do these tests work at predicting, for example, hip fractures and spine fractures compared to the clinical standard DEXA, and can we implement this clinically? And then on the right, of course, you can see once you make finite element models, you can do all sorts of things with them. On the right here, you're showing a simulation where we've virtually placed a pedicle screw into the vertebra, and you can estimate if that screw is going to loosen. So what I'm going to show you is interesting technology. It's been around for a while. The reason we're really talking about it today is clinically we can use it on existing CT scans, and so I'll mention how we got there along the way. So you don't have to have a dedicated CT scan for this. If a patient has had an abdominal or pelvic CT scan because of stomach pain, you could then repurpose that CT scan to do this test for them to assess for osteoporosis. And that's a very unique capability in the practice of medicine. Mostly in the practice of medicine, when you make a diagnostic test, the test is ordered specifically for that diagnostic test, and there's no reusing previous samples or previous images. And that is a big plus on the one hand, because we can be very efficient by repurposing a previously taken CT, but it actually presents unique logistical challenges, because certainly in the United States at least, the system is not set up to repurpose anything. All right, so let's go back and let's do some basic science. Here is the Surgeon General of the United States definition of osteoporosis. So a skeletal order characterized by compromised bone strength associated with an increased risk of fracture. So weak bone, increased risk of fracture. International Osteoporosis Foundation says it's a condition where bones become thin and lose their strength. So the two definitions by these major bodies, when they talk about osteoporosis, the term they use is bone strength. Although, as I mentioned, the de facto clinical test is a measure of bone mineral density coming from the DEXA scans. And so clinically, most physicians think of osteoporosis as having a negative test or having a positive test from a DEXA exam, but from a physics and biology perspective, it's about, can you detect if there is weakened bone associated with an increased risk of fracture. So as you get older, if you look at the top two sections on the right, these are micro CT scans of two cadaver vertebrae looking at a thin section, a thin frontal section. And you can see the trabecular bone. The black would be filled with bone marrow. And as you get older, on the right, you see you lose a lot of the trabecular bone. So you end up with loss of connectivity of that lattice and big gaps opening up. So there's also, as you can see, the bone flares out. So there's subtle changes in the external geometry of the bone as well. So this is what's happening as you get older. Osteoporosis at the spine and these changes in the spine happen to everybody. The question is, how far does it go? And then on the bottom, you can see two femurs. These are computer models using finite element analysis to simulate a sideways fall. And so the femur is loaded at the femoral head, and it's supported on the greater trochanter on the bottom surface. And what you're looking at are regions of failure. So red means that the bone tissue has failed in tension, and blue means that the bone tissue has failed in compression. These simulations that are done on the femur are based on micro CT scans. The models have about 500 million pixels or voxels in them because they're three-dimensional models. You're just looking at one section here. And each voxel has multiple degrees of freedom. So there's over 1 billion degrees of freedom in these models. So 500 million finite elements, for those of you who are into finite modeling. It's a nonlinear analysis with material nonlinearity and also geometric nonlinearity. If you look in the trochanter region here closely, you'll see on the bottom right-hand image, you'll see there's buckling going on of some of the trabeculae. So these computer simulations, very few people in the world can do these because of the complexity, the numerical complexity. We use Unique's parallelized code to do this. But what you can see from the failure regions is, if you look on the right femur, there's not that much coloring of the tissue. So actually, when the whole femur has failed, we're simulating these up to the point where the femur is just about to break. So when the whole femur has failed, not much tissue has actually internally failed for the bone on the right, which turns out is a very weak bone. And the bone on the left, which is a much stronger bone, requires a lot more failure of tissue. And that concept is one of structural redundancy. What you see in the stronger, healthier bone is there's lots of trabecular bone there and cortical bone to share load. So if there's failure locally, other tissue can step up and take the load. So in order to fail the whole bone, you actually have to fail a lot of tissue. But with the weaker bone, there's much less tissue, and once some of it fails, it's over. There's no redistribution of anything. So you've lost structural redundancy. And so we believe that's a very important element of bone fragility when you get older. It's not just that you've got less tissue, but as you get into having very little tissue, you run into this problem of losing any structural redundancy, which means the bone becomes very fragile. So that's the underlying physics of say, hip fracture. And in developing those computer models, we did mechanical testing of the very same femurs, and you can see that the correlation between the mechanical testing, which is on the vertical axis, and the predictions from those high resolution finite element models you just looked at, very, very high, which tells us that when you capture the microstructure, you essentially capture everything you need about the bone. Those computer models all assume that the bone tissue itself has the same material properties. That does not vary either within the bone or across the bones. And this is the result of the predictions under that assumption. So it's suggesting, at least in these cadaver bones, that variations of the tissue level material properties of the bone tissue were not important. And what really differentiated the strong bones from the weak bones was the overall size of the bone, the geometry, and the spatial distribution of the bone that can be detected on a micro CT scan. So that's an important result. Now, still looking at that, here's a few different bones from that study, and you're looking at that last frame where we can see the amount of failed tissue just at the point where the bone is about to break. And I've ordered them from top left to bottom right, from the weakest bone to the strongest bone. And the numbers here are the breaking strength of the bone as determined from the experiments. So this is, on the top left, it's 950 newtons. And on the bottom right, that should be kilonewtons on the bottom right, it's 4,800 newtons. So you're going from about 1,000 newtons to about 5,000 newtons. I'll show you some data later, but it turns out that once you go past about 3,000 newtons, once you fall below 3,000 newtons, the risk of fracture is quite high. Once you go above about 4,000 newtons, the risk of fracture is very low, and there's a transition between 3,000 and 4,000 newtons. So the blue stars are bones that have a strength between 3,000 and 4,000 newtons. This bottom star here has a strength above 4,000 newtons, and the 4 red stars are bones that would clinically be at high risk of fracture. And if you look at these pictures, what you can see is when you're at high risk of fracture, when the bone's about to fail, there's almost no failure of the cortical tissue. It's all in the trabecular bone. And the bone on the bottom right, that's the strongest, you have to fail a lot of the cortical tissue on that one. So the biomechanics are complicated in terms of how the bone is failing, cortical versus trabecular bone, the relative importance of those. And so the ability to predict who's going to fracture presumably will benefit from doing a biomechanical analysis rather than just measuring bone mineral density. So this is a lot of the basic science work that we've done along the way that ultimately informs the kind of technology that you want to use in the clinic. You cannot obviously generate these images clinically. These were taken with micro CT scanners. You need cadaver bones for that. So you won't get this spatial resolution clinically. But the question is, by understanding the detailed micromechanics, and when you use lower resolution models that are feasible clinically, can you ensure that you're capturing the dominant physics in your lower resolution models? So this is the kind of basic science work that is needed to validate and develop a more clinically feasible technology. And one last thing from this study. So in this study, I'm just, for one femur here, you can see I've colored the cortical bone in that kind of reddish color. And you're looking at a graph here of the bone mineral density as measured by DEXA on the vertical axis, and the femoral strength that's measured from cadaver testing in the lab on the horizontal axis. And so that those solid points, the black points, you can see there's a reasonable correlation between bone mineral density from DEXA and femoral strength. R squared is about 0.6. But you'll see on the top point that I've highlighted, there's a specimen. It's got a square box around it. It's got relatively low strength. In fact, it's the second lowest strength specimen, but it's got a pretty high bone mineral density of over 0.5. So it's an outlier on the graph, and so it's a specimen that looks like it's in good shape as far as bone mineral density is concerned, but it's not. It's a weak, really weak bone. What's up with that? Well, if it turns out, if you measure the relative amount of cortical to trabecular bone, so in the left image, it's the gray tissue versus the reddish tissue. So the relative amount, in fact, of trabecular to cortical bone, and the horizontal line in the graph shows when you fall below 1 on that, when you've got relatively less trabecular bone than cortical bone. That same specimen I just talked about is that open circle on the bottom there, and it's the lowest value. And so what this tells you is that if you're deficient in the relative amount of trabecular bone to cortical bone, that's bad news from a strength perspective. So it's telling you that internally, if the balance is off, if you just have a low amount of trabecular bone and you also have a low amount of cortical bone, so if the ratio isn't off, overall you'll have low bone mineral density. The problem is the bone mineral density is misleading if that ratio of trabecular to cortical bone is off. So even within the small sample of bones here, we had a very nice example of how bone mineral density can miss what's going on biomechanically. All right, so that's all the basic science. Question then is, so you're looking at those images on the left. If you dumb down the resolution to what you're looking at on the right, where you've got a fairly low resolution model, can you get useful information out of what you see on the right? And a group in Europe out of the Netherlands did these kinds of studies in the 2000s, and we repeated these studies for the spine, and it turns out, yes, you actually get reasonably good agreement. And if you just look at these images, the red regions are where you're getting failure on these, and there was a correspondence between where the failure is, even in that very low resolution image on the right, and the middle image you can see is somewhere in between. So I've got a date up here, 2003. In my lab, we had been doing very basic science work in the 1990s and early 2000s on mechanical behavior of trabecular bone. We did a lot of studies. How does it fail? How does it depend on density? how do you even do mechanical testing properly? So that was a lot of basic work we did in the 90s. We'd also been doing computer modeling, very sophisticated computer modeling, but we tried this voxel approach where you, instead of trying to model the bone with curved elements and use parametric, use quadratic finite elements, we just said, look, let's just use the so-called voxel approach, which is you make a finite element out of each imaging voxel. So there's a picture of a model right there. It looks kind of like a Lego model, and the colors here represent the different material properties we've assigned based on the underlying density in the CT scan. So a few folks had been doing that. Joyce Kiak, I mentioned Vera Hoop from Rick Huskis's group, Van Rietbergen at the time was doing it, and we have others in Europe who've been doing it since, and there's lots of people at this point who are doing final modeling of bones from CT scans. But we were surprised to find that it worked pretty well. In fact, we thought it worked really well. So on the right are some data. It's a small cadaver study. You're looking at the compressive strength as measured in the biomechanics lab against the finite element prediction. And you can see in the top left-hand graph, the R squared there was 0.86 for the small sample size. If you use stiffness, that's the top right one, instead of strength, so a linear model versus nonlinear model, about the same, not quite as good as the strength. So there seems to be an advantage of doing the nonlinear modeling. And then the bottom two graphs are just measuring things like bone mineral density from the scan, and they did not work as well. So the take-home message was captured in the title: finite models predict vertebral body strength better than quantitative CT. That was we felt that was a big deal, and that was 2003. And that's really what led us to starting the company Owen Diagnostics and getting serious about taking this to clinical practice. And it actually started where an executive from a pharma company, I presented this work at a conference, and he said, look, you know, we could use this technology in drug studies if we can track how drugs change bone strength over time. That might eventually speed up the regulatory approval of new drugs. Certainly, it'll help us evaluate new drugs during the development process. And that actually is what spurred us to start the company, so we could make this kind of testing available for drug trials and other research studies. So that was back in 2003. You can imagine that's when the paper was published. The work was actually done before then. I'll come back to that date later. So here we are today. In the United States, BCT, which is finite modeling of CT scans from clinical CT scans, just using that approach I just showed you. And we also measure bone mineral density, but that's available clinically in the United States as a diagnostic test. That's a big deal. I'll mention a little bit more about the pathway of this later. But right now, from the CT scan, you can measure bone mineral density. You can get at the hip the same kind of measurement you get from a DEXA scan. We virtually collapse the femur into a 2D image and just measure exactly what DEXA measures. We measure trabecular bone in the spine because you don't want the posterior elements in that model, excuse me. And then we have cut points for these, so we can tell you if you've got actually osteoporosis, defined as when these values are too low. And likewise, we can measure the breaking strength of the hip and the spine, and we can classify what we call fragile bone strength. That's when the hip strength or the spine strength is below a validated cut point. And the overall fracture risk is if you test positive for bone mineral density or you test positive for fragile bone strength, then you would be considered to be at high risk of fracture and have osteoporosis. So that's now a clinical test. And you can see two examples of reports for the spine and the hip. The way it works in the United States, at least, is that you send the scans to a centralized facility at Owen Diagnostics. They do the mechanical testing, or the BCT testing, and then they return the results to the physician who ordered the test, right? So it's almost like getting a blood lab done. This is the same delivery model that's used by HeartFlow, for example, for their FFR test from CT scans. You send the CT angiography scan to HeartFlow, they analyze the scan, they send the results back. So this kind of national lab model. The nice part of that is that you can pay attention to quality control, make sure all the tests are done consistently. You check the images, and so that's appropriate for the testing because it's not fully automated. There's a lot of things can go wrong with CT scans for those of you who have experience with this. All right, so along the way, lots of work went into going from the cadaver study that I showed you from 2003 to what I just showed you there, the clinical tests. So here's an example. So we had to repeat all that cadaver testing for the femur. And so here's some results for the femur. This is the finite modeling on the horizontal axis and the measured breaking strength from cadaver testing. This was done at Harvard, and there's no fiddling with the model here to make it work. This is, okay, we have this model, how did it do? And it did very well, as you can see here, strong correlation, and the line there is pretty much a y equals x line. So that when you say the strength from final model is 2,500 newtons, on average it is 2,500 newtons. So that was a nice study to validate the absolute accuracy of the measurements, and it's good for both sexes. We're interested in, can the BCT measure strength after drug treatment? So there's controversy that drug treatments change the molecular level, tissue material properties perhaps, and therefore this finite modeling technology, which doesn't have any kind of molecular level information in it, may not pick up what's happening with drug treatments. So this is an experiment we did on a 16-year-old, or yes, older monkeys, 8 to 19 years old, that had 16 months of treatment with a drug called denosumab. That's an osteoporosis drug. It's a pretty powerful drug that that stops bone loss and can increase bone strength. And it was compared then against a sham and a overactimized group with a vehicle. And the monkeys that had the denosumab, they were also overactimized to simulate osteoporosis. And so there was 3 groups of these animals. They were given the drug, and after the 16 months of treatment, all the animals were sacrificed. We got the vertebrae, and so these were data from the T12 vertebrae, and we did mechanical testing in the lab. And then before we did the mechanical testing, we did CT imaging. We got the images, and then we sent the images to Owen Diagnostics lab for analysis. And then the analysts at Owen Diagnostics were blinded to the mechanical testing results, and then everything was locked down, and then we did the statistics. And so here you can see the results. So the R squared here is, I don't think it's on the graph, but it's greater than 0.95. Very high correlation, and interestingly, the correlation didn't depend on what treatment group you were in. So what that says is the bone strength from the final modeling predicted the measured strength regardless of treatment. And that implies, just like that cadaver study I showed you at the very start of the talk for the femurs, it implies that anything that happened at the molecular level here was unimportant, that the models from the imaging contained all the information you needed to get a very good estimate of the actual strength. So this is the important study for showing that the final modeling actually captures treatment effects. Now, of course, the limitations are, well, that was denosumab. Maybe there's other treatments that do strange things at the molecular level. And of course, it's monkeys, it's not old people. These models were an attempt to get after an osteoporotic spine, but they're not the same as human vertebrae. So there's obviously some limitations with that, but pretty impressive findings from that. All right, so that's all researchy. Getting clinical, the question is, how do we calibrate the CT scans, and do you have to order up a new CT scan every time you do the test? And that's where we had to think about ways to work more directly with clinical CT scans, and we figured out along the way to calibrate scans rather than using an external calibration, is what phantom that you have to use in research studies. We use the internal tissues. So on the bottom right, you can see blood we're using from one of the aorta, just anterior to the vertebral body, and at the hip, fat. There's a fat pad deep within the pelvis that we can use. And you can see in that top image, there is a phantom calibration. So we were able to do direct comparisons, and we found that our Phantomless calibration works really well. So that was a big advance. And that means then that we can do the so-called opportunistic approach. That is, if you've had a CT for some other reason, you can repurpose that CT scan and do the BCT analysis just as accurately as you would if you had a calibration phantom. So that is what was a huge factor in making the technology feasible clinically. And it's an interesting example because as we tried to develop the test clinically in the 2000s, we realized it's a real barrier to entry and to utility if you're going to have to require everybody to get a CT scan, because people are concerned about radiation doses from CT scans when it's applied to millions of people in the population. So could you possibly not have to take a CT scan? And we were scratching our heads, and that's what we figured out, okay, let's try and see if we can do this Phantomless calibration. The Phantomless calibration had been around before, but it wasn't very precise, and so we figured out a way to make it very precise. So that's kind of an example of, we're focusing on developing a finite element technology, but in order to make it work clinically, we had to actually get into how do you calibrate CT scans. All right, here are some validation studies from that, and what you're looking at here is relation between different measures of bone density taken from, these are CT colonography CT scans, and on the left here is you're looking at DEXA measurements of bone mineral density measured at the hip, that's on the femoral neck axis, on the vertical axis, and at the spine. So when you do a DEXA test, you can do it at the hip and the spine. And typically with DEXA, the lowest T-score, the T-score is just a statistical way of describing the bone mineral density, and the -2.5 means you've got osteoporosis. If your T-score at the hip or the spine is less than -2.5, clinically you're said to have osteoporosis. And you can see on that scatter plot the relationship for patients between their hip and spine BMD T-scores is very weak. It's R-squared is just 0.36 here. So there's a lot of discordance between DEXA when done at the hip versus the spine, and that's just people. I don't think people appreciate that, but that's actually the clinical standard, and that leads to a lot of confusion. The middle graph, the right-hand graph, pop over to the right-hand graph, is just looking at the hip DEXA, but it's looking at your left hip versus your right hip. And you can see the R-squared is about 0.82. So that's typical scatter between both hips, whether it's real variation between the hips or just a measurement error. It's all combined in here. And then the middle is the left hip for DEXA, that's on the vertical axis, and the left hip from BCT analysis. So this is measuring bone mineral density from the CT scan in the same way, giving you the same measurement as DEXA. And you can see here the R-squared is 0.84, and your line along the line y equals x. So basically, the BCT BMD measurement is equivalent to DEXA. It's like your left versus right hip. And so this was an important study to show that the bone mineral density from the CT scans using opportunistic with internal phantom calibration is pretty much the same statistically as DEXA. And that's important because the clinical field is hooked on DEXA, and it's very hard to introduce a new technology without reference to DEXA. So for that reason, when we do BCT clinically, we always provide the BMD information as well, and we're not relying just on the bone strength because the physician's very comfortable with the BMD information. And that's an interesting lesson learned in terms of translation. You know, you've got something new, it's nice to bring along the old and familiar as well. All right, we do a lot of fracture outcome studies, and the most important one we did was what we call the FOCUS study. This was performed at Kaiser in Southern California, which is a large healthcare system. And it's got about, I think they have 14 major hospitals are part of that group, and it's full care within the United States. So patients get all their care at Kaiser, and they have a very tight record of patient medical records. So we were able to go back in time and said who had a CT scan in the last 5 or 10 years, and a CT scan that contained the hip for any reason, and then of those patients, how many people subsequently broke their hip. And so we identified those, and then we had a control group of people who had the CT who didn't break their hip. And so we were able to do a comparison of the BCT on the CT scans and try and predict who would fracture hip versus not fracture their hip. So it's a predictive study. It was blinded. We didn't know who broke their hip when we did the BCT analysis. But it's done on existing data. So it's kind of like it's not quite a prospective study, but it's got almost everything you'd have in a prospective study. And so what we found from that study, we confirmed that the BMD T-scores from BCT were the same as DEXA. We had a lot of DEXA information for all these patients. That the femoral strength predicted fracture independently of BMD, and we had higher sensitivity, and patients who tested positive with BCT were actually at statistically higher risk of fracture than patients who tested positive with DEXA. So this showed that BCT is at least as good as DEXA when using any old CT scan. I think there was 80 different CT scanners used in the study. Here are some of the results. These are the hazards ratios. So it's a measure of risk. This is hazard ratios. Let's see, hazards ratios for the continuous measurements. And you can see for the DEXA, if we start with DEXA here, the hazard ratio for women for the hip T-score is 2.3. So the outcome here is, did you have a hip fracture in the following 5 years? So that means that patients, for a change in measurement here of, I believe this is per standard deviation, the risk would go up by a factor of 2. And that was the very same as what you see here for BCT T-score. So very nice correspondence there. If you look at the men, it's actually numerically higher for BCT for the men. We also showed that the hazard ratio for femoral strength, 3.6, is statistically higher than it is for either of the DEXA scores, either using the hip BMD T-score or the combination of the hip or spine BMD T-score. That bottom one, the 1.7, that's the clinical standard. You usually have a hip and a spine measurement made, so you're always using the lower of the T-score, and that dilutes the measurement for predicting who's going to have a hip fracture. So this is very nice validation for that. The same trend for the men, but just not the same statistical power. There weren't as many hip fracture cases for men as there were for women. And also we showed that if you look just at the BCT data, femoral strength, this line here is, did femoral strength predict fracture independent of BMD? So you've got femoral strength and BMD in the model, and the hazards ratios for femoral strength were still highly significant. So this shows that femoral strength predicted fracture independently of BMD. So this was a big deal study. It's one of the biggest hip fracture studies ever done because there was so many patients that had hip fractures. Usually in hip fracture studies, there's 40 or 50 patients with hip fracture. We had hundreds of patients with hip fractures for each sex in this study. So we've repeated those kinds of studies for the hip and the spine. The focus was the biggest, but there's what you see here is hazards ratios when measurements are made of the hip for predicting, on the right hand side, hip fracture, or this one in the middle is called MOF. That's a major osteoporotic fracture. And you can see the blue is the hazards ratios for femoral strength, and the gray is the hazards ratio for bone mineral density. And every case, the blue is, except for this second one where they're almost identical, the blue is to the right of the gray, which means that the hazards ratios were higher for strength than for density. And on the left is the same thing for the spine, for predicting measurements made at the spine for predicting spine fracture. And again, consistently across every study, bone strength is better than BMD. Every single, much stronger effect in the spine than at the hip, but very consistent findings. So this is convincing. And here's what happens when you've got measurements of strength and BMD from the BCT test. So all these measurements are taken from the CT scan. If you plot them, this is a study we did in Iceland on the ages cohort. There's a decent correlation between strength and BMD when everything's measured from the same CT scan. But here, the open circles are the patients who had a hip fracture. And you can see in this gray box, those are the patients that BMD misses that bone strength picks up. So that's kind of what the test is giving you extra. And if you look at the box in the opposite corner there, there's no circles in there. So in the AGES study, at least, the bone strength would pick up a lot of extra fracture cases than BMD, and that's how the bone strength can predict fracture independently of the BMD. We've done cost effectiveness studies, and they predict that if you had, say, 1,000 patients who had CT scans, typically only about 10% of those patients will get tested with DEXA. So if you were to follow the 1,000 patients to see if you could identify who had osteoporosis and treat them and prevent a fracture, after a few years, how many fractures would you prevent versus, so if you did that 1,000 patients with BCT, so you'd be able to test nearly all of them, versus usual care, only 10% per year would get tested, and then that would start the treatment pathway. What you see is that BCT is highly effective. So it's predicted to prevent more than double the number of hip fractures than usual care for women, and way more in men, because men are woefully disregarded currently in clinical care for osteoporosis, and quality of life is also substantially improved. So if you could somehow make sure that most patients who are eligible for testing, who have a CT scan, existing CT scan, if you could arrange that most of those get tested, it would have a substantial impact on fracture prevention for osteoporosis. I mentioned at the start of the talk, what started the company was this interest from drug companies in being able to track bone strength during drug trials, and we've actually done a whole bunch of studies on that topic and related topics over the years. So it's been heavily used from 2007 all the way up to monitor patients with treatment. Almost every single treatment that's used for osteoporosis has been assessed. And here's an example of some results. So this is a fairly recent study on a drug called romosozumab, and it's compared it with a teriparatide. Both of these drugs are anabolic. They make new bone, and placebo. So these are postmenopausal women given this. After 12 months, you're measuring changes from baseline for the different drugs and the placebo. If you look at the right, you can see that there was a large change in strength for romosozumab, and then that was statistically higher than for teriparatide, and both of those were much higher than placebo, where there was bone loss. And at the hip, there was a significant change for the romosozumab and no significant change for the other groups. It's interesting, on the spine, you can see the strength change is on the order of 20 to 30% with the drug, with the Roma drug, and about 20% for teriparatide. But the hip, the changes are much smaller, so on the order of 3 or 4%. And we're currently doing research to better understand how can small changes in femoral strength, these are average changes, how did they lead to fairly large decreases in fracture risk? The decrease in fracture risk at the hip is about 50%. It's about 70% at the spine. But still, how do you get a 50% reduction in risk of hip fracture if the bone strength on average is just changing by on the order of something like, we'll say, 3 to 5%? And that's an ongoing topic. That's something we want to explain. And then one last thing on monitoring. It's interesting, I mentioned DEXA before. DEXA has issues with the spine particularly, and what you can see is if you monitor changes in drug over time, so this is percent change in bone strength over time, up to 2 years. This drug is called odinecatab. It's another osteoporosis drug against placebo. If you look at the DEXA, the odinecatab gave you a nice response over time, and the dashed line is the placebo. It showed, almost no changes. But if you look at the BCT on the right, and what was happening in the placebo group was there was a lot of bone loss, of strength loss going on that was not picked up by the by DEXA. The effect was there at the hip too, but not as pronounced at all. The issue is mainly at the spine, and this shows the limitations of DEXA for measuring bone loss, for example. And so definitely, if you're interested in what's really going on in your spine, you would prefer to do BCT and not just do DEXA. All right, I'm going to wrap it up there, and I'm just going to make a few comments. So pathway here going from bench to bedside, the first paper that really kicked this off, even though there was a lot of lab research going on in the decade, in 2 decades before 2003, that's when things kicked off about clinical translation, when we thought we had something at the bench that was worth bringing to the bedside. And here we are almost 20 years later. Now, COVID has delayed things in the last couple of years, but it's been a long way. And so what took so long is you're developing the technology, but you also have to develop the science, especially here where you ultimately have to use a lower resolution image, but you have to be confident about the science that you're left with that lower resolution image. Lots of clinical validation, fracture outcome studies to prove that we can predict fracture, even if we're using retrospective data sets. Very timely, huge efforts there. We've done, there was nine papers published on fracture outcome studies between the hip and spine. That's a tremendous amount of work. Regulatory use, if you want to use this for diagnostic use, there's a lot of regulatory hurdles. You have to prove to the regulatory authorities that you can predict fracture, that diagnostically you've got cut points that hold up, that are robust. That's much higher bar than if you just want regulatory approval to just make the measurements. Diagnostic use means that you're going to base medical decisions on the results of the test, and that's different than screening. You'll see a lot of AI applications where people just want to analyze every single scan you've got and identify people at high risk for a certain disease. That's kind of, I call that case finding. That's not diagnostic use. You can't use those measurements to treat patients. You have to have a more formal diagnostic test for treatment. Logistically, how are you going to deliver the test? And we've decided, at least initially, on this lab model where you send us the scans, and that shifts the onus over sending us the scans. Now we're into this whole business of health IT. How can we streamline sending scans around from PACS, getting through firewalls, getting permissions? If you were to sell software, then you're into issues of robustness. Can you be confident people are using it properly? If it's fully automated, remember, you can automate so many things, but the question then becomes is quality control, because how do you check that your automated analysis is really accurate? Again, that's very important for individual patient care. And now, so we've checked off all of those. They're all done in this time frame. But now we're into just classic awareness and utilization. Can you get physicians aware that this test is available, and can you get them to use it? And that's classic, marketing, education, and that's what are the next steps with this. So hopefully that gives you a sense for the journey here, and I hope that's interesting for you, even if you're not doing anything to do with bone. Any application, you get this sense for generally what's required for the whole big picture. With that, I will open up to questions.
Thank you so much, Professor Keaveny. That was a very interesting presentation, and mind-blowing results, I would say, and also a very nice summary that you had in the end. And as you said, this is not necessarily specific to bone, but it is, applicable to a lot of fields related to in silico medicine and in silico modeling. So yeah, attendees, please ask your questions in the question box. I have already a couple of questions from my side that I can ask, and I have one question at this moment in the question box. So, oh, another one also came. So we have 3 questions at this moment in the question box. So I start with the question. The first one, Mojtaba has asked, thanks for the presentation. As I know, bone mineral density for vertebra gets evaluated in lumbar spine. If spine implantation ends in thoracic region, how can we find screw pull-out force in thoracic vertebrae since there is not enough information?
Very good question. So yes, the osteoporosis test we do at the spine, we analyze. In preference, it's L1, T12, L2, or L3. And the cut points we have are specific to that. When you go to other levels, you have to grapple with, okay, so I have to deal with other cut points. That requires additional studies. You've either got to somehow translate your cut points from one level to another. If so, you've got to validate how you do that. And so that requires some extra development work on that front, and we're working on all of this, but you have to go then and convince people that it'll predict fracture. So we've done one study, for example, with the Framingham cohort in the United States, where we did measurements at T9, and that worked very well. So I think we will be getting to that point where we'll have a preferred level in the thoracic region that you can go to. But your question goes beyond that. It's asking about pedicle screws, for example. So with pedicle screws, we've done some work in this. It's not published. It will be soon. Yeah, you have to go to the level where you're sticking the screw in. And again, you can make your predictions. The first thing that'll come up is, does it predict clinical outcomes? You need to do a clinical study for that. You need to do a predictive clinical study. In other words, you can't just do a study where you get the results and then you fudge everything to make it work. I call that a calibration. You have to do a study after that on a separate population to convince yourself that there's some generality here. And then ideally, you would do some cadaver experiments. You would do pull-out experiments in cadavers, and you would, like we did our cadaver experiments for the breaking strength, you would want to show that your predictions of pull-out strength, for example, for a pedicle screw, are strongly correlated with direct measurements from the spine. So there's all those steps we mentioned for predicting hip fracture and spine fracture. They have to be repeated to get something that's really robust and believable.
Thank you for the answer. Enrico has asked that first said, thank you for the great talk and impressive journey. You haven't mentioned much about the loading condition simulated in the femur or vertebra. The fracture risk will also be affected by the loading direction, by, for example, fall direction for femur, lifting weights for vertebra, etc. How sensitive are the models for this, and can the models do even better by taking into account for critical loading as you have validated mechanistic models?
Yep, very good question too. You guys are super sharp. We've been looking at this for a long time. Others are looking at it too. Marco is looking at this a lot. The interesting thing is, back in the 90s, we thought maybe it's all about how you fall. I did my postdoc in a lab in Boston with a guy called Toby Hayes, and that was his big thing. It's how you fall, soft tissue, all that sort of thing. The bottom line is, the fact that bone mineral density is associated with risk of fracture says that it's not dominated by the loading conditions. If it was dominated by the loading conditions, your bone mineral density wouldn't be predictive of fracture. So that's an important thing to keep in mind. But our work has shown that if you take a femur and you load it multiple different ways, and you do that for 1,000 femurs, what you'll find is there's a pretty strong correlation between the strength of the femur for any one loading condition and some other loading condition. And so from a statistical perspective, we haven't found anything so far where using multiple loading conditions helps with the prediction, because using one loading condition is quite strongly correlated with what you'd get for that patient across the others. That said, we're still looking at it, and others have found maybe there are some advantages to it, and people are using machine learning and neural networks to try and, you know, discover something there. So that's ongoing. As far as patient prediction, oh, can I predict how you're going to fall? No, you're not. You're not going to do that. So there is an inherent uncertainty here that you just can't overcome. And so it remains a topic of research to see if going beyond what we've done improves prediction, right? Clearly, if you could tell me the way somebody would fall, and if I could put that into a model, that should improve things. But what I'm saying to you is, I don't think you can tell me how somebody's going to fall with any level of confidence that it would make the prediction improved. So that's kind of where we are on that. It's a very interesting theoretical point, but I think it's not clear. It's not clear. It's actually going to improve things.
Great, thanks. Another question from Mark. Thank you for the great presentation. You assess bone strength accurately. Do you also control for load variations between patients when assessing fracture risk during a lateral fall to the greater trochanter? The resultant load will depend on a patient-specific and fall-specific factors like level arms, structure and material properties, tissue thickness on the trochanter that could be taken from CTs.
Yeah, so some of what we just talked about still holds, right, in terms of how you fall, that sort of thing. That I think is probably intractable. Soft tissue thickness is for sure something that we can measure, and that we are looking at that. There is research out there showing that soft tissue thickness can help, DEXA studies, for example. I expect it to be a nonlinear problem. My sense is if your soft tissue thickness is very thin, it's going to put you at higher risk. Once you go beyond a certain point, you're going to be protected, and it won't matter how thick the soft tissue is. So that is another topic of ongoing work. But you're absolutely right. The information is in the scan. Hopefully, we can utilize it, and hopefully, it will help. Some of the other factors, as I said, if you can't make a good measurement of something, then even in theory, if a factor is important for fracture, if you can't make a good measurement in a clinical context, then it's not going to be useful for prediction. But we're trying to get estimates of people's risk of falling, and that maybe from the medical record. If you watch somebody cross the street, if you watch an old person cross the street, you can tell at a glance if they're at high risk of falling. You'd kind of like to get a quantitative measurement of that into your algorithm. How do you get that? An objective quantitative measurement that says this person is at high risk of falling versus this person is at low risk of falling. The 75-year-old who's out playing golf or tennis or going for walks every day versus the 75-year-old who's sitting at home and who can't even walk. There's got to be a way to bring that into the algorithm because it has to be relevant.
Cool, thanks. The next question is from Daniel. It was a very interesting presentation. Congratulations. The fact that the hospitals must send the images to the company raises any concern with the privacy policies? Should the data be randomized?
Policies are a little different in Europe and the United States, so I don't know the specifics of Europe. But let me, in the United States, no, there's lots of agreements need to be put in place to protect patient identity. So for example, the company where we do this, there's just a lot of guidelines and constraints on what we can do. And so that's taken care of with appropriate controls and regulation. But it is a barrier. I mean, there's a big process where you're working with a hospital for them to review your security, your procedures, to ensure that it's okay to do that. And then for data usage, there's all sorts of restrictions on that. It's just for healthcare. So those are very doable things. And of course, the way everything's working now is with the ability to share data and huge databases. There's going to be more and more centralized sharing of data and analysis of data in healthcare. So I think the writing's on the wall that this sort of thing, even though it's a little bit slow now to get up and going because of these regulatory issues, that will be sorted out sooner than later, and they will cease to be issues. They'll just be procedures that you need to follow.
Cool. So the next question is from Carla. With respect to the Phantomless calibration, that potentially adds additional patient inputs beyond the focus on the bone? Have you investigated, or do you plan to investigate how that impacts the fracture risk prediction?
I'm not quite sure. I'll try my best to answer that question. I think you're saying if I was to, for example, calibrate the scan different ways, how would it affect fracture prediction? And I don't have an answer off the top for that. It could be that you could do a poor calibration and maybe capture still enough of what's going on that you could get a reasonable fracture prediction. So we just haven't gotten into that. Part of what we're doing is producing measurements of bone mineral density, and for that you need to have as accurate measurements as possible, because you want confidence that those density measurements aren't going to be completely different the next time you assess that patient, right? And that you can compare them with DEXA. So the calibration is very important for that. It's definitely possible that you could, for example, add a random error to all your measurements and still end up with a reasonable fracture prediction. It won't be as good, but it still could be possible. And that's true for everything. But we haven't done those studies where we've perturbed things and said, how does that change the fracture outcome? We just haven't done that.
Yeah, thanks. The next question is from Mohammed. He has asked that, do you think in order to complement or replace the DEXA exam, VCT would need to be automated to a level that it can be performed by the CT operator without requiring all the finite element modeling expertise?
Who knows? You know, as I said, you can automate on a computer. You can automate most things, right? It's going to be an issue of have you missed some cases? You know, your algorithm just does this, but it shouldn't have done that, and no one's looking at it, so you don't even know. That's the problem with individual patient care. If you're doing population type studies, you'll find, you know, you read these studies, oh, we did 25,000 patients and we showed this risk. You get away with that, with missing individual patients and that, because your sample size is so big. But for individual patient care, the quality, I think, is critical. I think what is going to happen is, as we go forward, there will be more and more automation. But I think for clinical care, you have to really watch. Then the quality is what you have to watch. So yeah, maybe in a few years, this thing will get to a point where it's more automated. But you know, again, the centralized lab, we do that with blood. It's happening in other applications. I think it's a reasonable model, rather than just throwing it out there and hoping that folks on the point of care side know what they're doing.
Great. The next question is from Lodovic. How were the interventional thresholds for your BCT strengthened measurements calculated?
Yeah, so we actually developed those with a very pragmatic approach. We said, look, you know, bone density is an important predictor of fracture. It's well established. With these DEXA scores, there's established cut points. So we determined just from statistical analysis what are values of bone strength that correspond approximately to the values, the cut points of BMD. And so we just did that with data we had, and then we said, okay, those are the strength cut points. And then we went out to, so we said, that's it, this is what they are. And we rounded them off to round numbers. And then we went out to the fracture outcome studies then and evaluated those cut points. So it was a kind of we prescribed what they should be based on the correspondence with bone density. And then that was that. And then we just went out and evaluated them. As opposed to saying we did a fracture outcome study and then we chose a cut point to make things work. We did not do that. All the fracture outcome studies were used to validate what we had previously chosen based on that correlation.
Great. So the next question is from Naya. So many questions, Professor Keaveny. The next question is from Naya. Are there any works conducted on MRI images to assess bone strength?
You know, there might be. I'm not fully up on that, I have to admit. The problem, so if MRI is at very high resolution, you can actually see the bone. It's a negative image on the MRI, right? But it has to be very high resolution, so it's hard to get that with MRI. Otherwise, MRI doesn't tell you anything about the level of mineralization or bone mineral. So that's very important for bone strength. So I think MR can give you some aspects of geometry of bone. If it's very high resolution, you can actually see the microstructure, and therefore you might be able to assess something. But otherwise, I think it's very challenging to do this with MRI.
Great. The next question is from Samuel. Do you ever reject patients for assessments due to comorbidities? For example, in patients with evidence of bone marrow lesions?
Yeah, I don't have a straightforward answer for that. If we got a clinical case to analyze and it had some really weird stuff going on with the bone, yeah, in some cases we may not analyze that. If it's the spine, for example, if I saw L1 had some crazy lesion in it and L2 looked normal, we would analyze L2. So that would be the kind of approach. And there is interest in doing the test specifically on bones with lesions. And so that's a work in progress. Again, you would like to do clinical studies to show that in patients with lesions, you can predict who's at high risk of say, pathological fractures. And again, people are beginning to do a little bit of that. But in theory, it should work fine. But generally, yeah, if we encounter a bone that has very unusual morphology, we'll try and go to another level. We can certainly analyze it. The question is, how would you interpret the result?
Great. And the last question is from Milton, which is related to which FEI solver do you use? And I can add, my question to that, because I was really interested in the simulation that you showed from the study back to 2014, I think, that you said that you have simulated it with, billions of degrees of freedom on parallel code. So actually, I was also interested to know about the HPC setup that you use, number of cores, and that was amazing.
So for the clinical work, we have our own solver that we wrote, but it's fairly routine. You could use, if you wanted, you could to do the clinical, you could use a commercial solver. We have 40, 50, 60,000 elements in a model, very, very doable. The ultra high resolution, yes, that is we developed a custom code, massively parallel code. I think it could partition up to 1,000 or 2,000 parallel processes. So it's a lot of partitioning going on. And we developed that back in the 2000s. We won some supercomputing award for that, for scaling. It's work I did with a fellow called Mark Adams and one of my colleagues in math department and computer science, Jim Demmel, and Panos Papadopoulos, one of my finite element expert in mechanical engineering at Cal. So those guys, that's what they do. And we continue to use that. It's used on a cluster in Texas that the National Science Foundation funds. So it's a national cluster. It's very fragile. We had to recompile it over the years, which was a massive project, and we haven't touched it otherwise. So yes, that's kind of like a treasure. And in fact, though, it's kind of nearing its life because I'm not really doing that computation in my lab anymore, and I'm not sure if I have any more grad students in that area. So So that may be going away. But yeah, very unique, very challenging to set up. And if you look up some of my papers from around then, you'll get more information on the details of that. Yeah.
Sure.
Around 2004, 2005.
Yeah, that's amazing. Yeah. Okay. So thank you so much, Professor Keaveny. There is no further question here. So also thank every attendee to be here. And yeah, we can end the session. Well, it was a great pleasure to have you, Professor Keaveny, here with a very nice talk that you had for us. Thank you so much.
Great, thank you. And if anybody ever thinks they want to work with me, or you're in that, send me a note, or at least in the future, keep an eye on things, and hopefully we'll move all this together.
Yeah, sure. Thank you.
Bye, everybody.
So, bye, everyone. Bye.